So, hi everyone, thanks for coming to my presentation. I'm going to present what we've done for Kohaku wallet in terms of post-quantum integration. Before I talk about post-quantum cryptography, let me just briefly present what is my company, ZKNox. So we are only 3 people. Nicolas Bacas, that you probably know from Ledger because he was the co-founder of Ledger. He's a specialist in hardware integration and hacking this hardware device. And then Renaud and I are cryptographers, so we work mostly on cryptography, I would say. And with ZKNox, we try to work on every layer of the blockchain, from hardware integration, smart contract. We try to focus on every layer of the blockchain. So in this presentation, I'm going to talk about a bit of hardware wallet. I have my ledger here. We provide, in this work, the first implementation of post-quantum signature inside the hardware wallet so that the secret never leaves the secure element and you can sign without using the software. And I'm also going to talk about smart contract because we provide the first signature verification inside the smart contract that fits for transaction in Ethereum because we have a limit in terms of gas, and so we provide the first optimized smart contract for post-quantum signatures. So if you need to remember something, it's that for now on the execution layer, it's already possible to have post-quantum security. Of course, it's a bit expensive, as you will see, but it's already possible. If you want more information about ZKNox, we try to provide some demonstration of what we do in terms of implementation and deliveries. So yeah, feel free to check it out. So Kohaku is a SDK pushed by the Ethereum Foundation for focusing on privacy and security for the wallets. Actually, there is a presentation by Nicola Consini just right now, so you won't be able to attend it. But if you stay after my talk, there is also a presentation by Stefan on Trustlet Manifesto here. And yesterday there was also a presentation by Renaud on hardware integration for privacy protocols. And this talk is using a smart account that is not included in Kohaku for now, but it will be integrated soon, and as long as we have smart account, we will be able to deploy this post-quantum accounts. So you can also check the GitHub of Kohaku if you want. So why we need post-quantum security? On Ethereum, we rely on ECDSA, meaning that when you want to sign and send some funds, you need to provide an ECDSA signature. So it's a very nice signature that has very nice properties. First, they are small, around 60 bytes. It's also very efficient, so you can verify the signature efficiently, and it's quite trusted because Bitcoin, Ethereum, and most of the blockchains, they use these signatures. The only small issue is that it's broken if you have a quantum computer. So actually there was 2 papers that were published yesterday about how to optimize this quantum algorithm, which makes ECDSA a bit trustless now. But we have some alternatives for this issue. And since almost 10 years now, there is a standardization process by NIST so that we have different algorithms to be resistant against a quantum computer. So there have been many candidates for being post-quantum. Some of them have been broken, and some of them are still secure. And actually, the NIST, the standardization institution, selected 3 candidates that I will be presenting here. And many institutions, including Ethereum, announce some post-quantum integration so that we can resist this issue of quantum computer. So also here you can check the post-quantum roadmap for Ethereum, provided by Justin Drake if you want. And yes, let me introduce the 3 candidates. So there is actually 2 candidates based on lattice-based crypto and 1 based on hash functions. And you can already see that there is a small problem. The signature size and the public key size is at least 10 times bigger than for ECDSA. So this is an issue for a blockchain because we want to store on-chain this data, and this will make big data on-chain. These numbers, I will go back to them soon, but it's the gas code that you need to verify a signature on chain using our Solidity contract that we provide. So in this talk, I'm going to focus on the two first columns because the third one has huge signature size and it's not really designed for blockchains. There are other properties that we want from the signature. For example, we want to be able to integrate this into a hardware wallet because people use hardware wallets. And actually, for some of the signature schemes, it's quite complicated to get this fit into a hardware wallet. So in this talk, I'm going to show you how to sign using MLDSA on a ledger device. There are other properties that I won't dig into the details, but we want to be able to do public key recovery to reduce the data on chain. Threshold signature is also something nice that we would like to do in the post-quantum world. So besides this implementation, we also push some EIPs for these two candidates. So one EIP is about MLDSA. So we provide two precompiles, one for the NIS version, so complying fully to the standard, and another version changing the hash function. Anyway, I won't go into details on this, but we did some optimization so that the public key can be expanded to save some gas in the verification. Basically, the public key is 1 kilobyte, but we expand it into 20 kilobytes, which is even bigger. But then we save some computation in the verification. The second EIP is for Falcon, so the other candidates. And here it's a bit different. We provide two EIPs because the verification has a clean separation between hashing and verifying using entities. So we provide two precompiles so that we get something more modular. At the end, what you need to remember here is that a verification of a post-quantum signature is basically a few hashes and a few entities, which is not too expensive at the end once we have some precompiles. So now that we have our two signature scheme, it's also important to be able to handle the keys properly. So you probably know that there is something called BIP32 for deriving your secret key for ECDSA from your mnemonic phrase. So basically you have your mnemonic phrase, you hash it several times, and you'll get some bytes that will be your secret key. What we provide here is a simple way to have post-quantum keys, just having another keyword so that at the end you will derive different keys, some for ECDSA, some for MLDSA, some for Falcon, etc. So now how do we integrate this into Ethereum in the execution layer? Let me explain how it works in practice when you send a transaction. So Alice wants to send some ETH to Bob's. She will first create a signature of a transaction hash that contains all the information of the transaction. And this signature will be verified at the consensus layer using the verification of the signature ECDSA. Something that is really nice in Ethereum is that we have smart account, which means that this verification can be done inside a smart contract. So instead of having this verification of ECDSA, you can basically put whatever you want. And in this work, we implement post-quantum verification inside this smart contract. So using this structure, we can enable post-quantum security using smart contracts. So actually, we don't remove ECDSA and put MLDSA, but we rather put a hybrid verification with two signatures to be verified. So one ECDSA and one could be MLDSA or Falcon. So I'm going to show you a small demonstration where I first create the smart account. So from your externally owned account, you create the smart account using the generation of the keys and then storing the account, including the public keys. And in the second time, I will show you how to make a transaction using a hardware device. So now we don't really need the externally owned account. We will just send some fund from the smart account to another account. and hopefully it works. So let me show you the website. So also you can try it on your laptop if you want. So here I have the first step is to create my account. So I will show you in software. So I write my mnemonic phrase. Of course, it's not the real one. So for now, it's connected to my Rabi account so that I can create this smart account. So this is deploying the account. So what is happening in backend is that it derives a secret key for ECDSA and for MLDSA, and then do the key generation, storing, creating the smart account, including the 2 public keys. And here we have the address of our smart account. Now if I go in the send transaction section, so this is the address of my smart account. And now I'm going to send to, let's try with Vitalik. Actually, I don't know if it's going to work with the ENS, but let's try. And yeah. And I could do it with the software, but I will try with a ledger. So I will sign using the ledger directly, which has the same mnemonic phrase, yellow, yellow, yellow. Yeah. Okay, so now it's asking for the ledger. Use in clear signing, so I can see exactly what I want to sign, including the recipient address, the amount of tokens. And now I sign, submitting to the bundler, and now the transaction is accepted by the chain, so we need to wait a few seconds. Let me go back to the slide now. So just to conclude, we provide a smart account with post-quantum security in this presentation. I provide here the gas cost. So you see that it's quite a lot of gas because it's in millions of gas. This is because we have huge public key to be stored in the smart contract. But still, it's something feasible because depending on the context, you would spend a few dollars to send a transaction if you want to secure your funds against a quantum computer. Still, it's not production ready because we have to audit the code. We would like also to have some version of higher security level. We provide the first post-quantum signature implementation fully on a hardware device. For Falcon, it's still close to the limit of 40 kilobytes, so it's quite complicated to implement it. And what is also missing is precompiles, because using a precompile, this cost for sending a transaction would be reduced a lot. Other things that are missing to get fully quantum security is the deactivation of the EOA, because once we create this smart account, we still have a way to revert this creation. So using the EIP 7851, we would get full security by deactivating the EOA. There is also an EIP for the frame transaction, which is a kind of standard for the smart account specification. And about the precompile that we would like to be pushed, we propose 2 precompiles that would lead to very small amount of gas. But we also provide another precompile that is more generic with Vitalik. As you can see, it's more gas to be spent, but the main point is that at the end, the cost of the verification will be mostly the data call, storage, and copy. So I wanted to highlight this and give you like a lower bound of how much gas cost you will need for the data storage. So if you use Falcon and ECDSA, just storing the signature on-chain, storing the public key and sending the signature would spend at least 17 kilo gas. And for MLDSA, you would have a cost of at least 46 kilo gas. So at the end, the verification itself won't be the big cost of the transaction. And just to go back to transaction. So now we have the transaction that is on chain. So I can just check it. On Sepolia. And here you have the transaction that I've done to Vitalik. And you can check the details. So you have the gas cost here. And you can get more information on the smart account transaction here. Yeah, that's it. Thank you.
Does anybody have questions?
It looks like you. Yeah, thanks for the talk, and it's also an amazing work. I assume everyone here agrees. My question is, it looks like the post-quantum signature scheme you are using is the top two recommended by the NIST, but they are all lattice-based, right?
Yes.
And I assume the according Stroman map or something like that. Ethereum Foundation maybe prefer to go for totally hash-based version, right?
Yes. So in the in the roadmap of the Ethereum Foundation, they focus on the consensus layer and the execution layer. And for this work, it's only the execution layer, and we focused on the lattice-based scheme because we consider that following the standard is also something that we must do, and using hash-based signature is a really huge signature that would make it very expensive to verify on chain. Yeah. So yeah, on the consensus layer, it seems that using a hash-based solution would be better, but for the execution layers, we believe that this would be the best fit to follow the standard from Web 2 and to get something secure. Yeah.
I think that's all. Okay.